right. So hello everyone, and welcome to the first edition of the MTL NLP Meetup events in 2021. So first of all, Happy New Year, everyone, and hope your year has started. You have started a great year ahead of yourself. So today's event is on the topic of annotation and knowledge extraction, and we have three great speakers joining us from Montreal and Verona in Italy. And I'm really looking forward to those interesting talks. So before I pass the podium to the chair of the event, Dr. Leila Koustuv, I would like to mention a few things that I usually mention, which is please during the presentations, in order to help the focus remain on the speakers, please turn off your cameras and your microphones so that everyone can enjoy the talks. So now the floor is yours, Leila.
Thank you, Hassam. Can you hear me well?
Perfect.
So I'm very happy to chair this meetup today on the topic of annotation and knowledge extraction. We have three talks. The first one is from Marco Rospocher, I hope I pronounced this right, who's associate professor at the University of Verona in Italy, who will talk to us about joint posterior revision of NLP entity annotations via ontological knowledge. Sounds interesting. The other talk will be from a PhD candidate at McGill and Mila, Koustuv Shinan, I hope I pronounced this right, I'm sure I'm not, who has an interesting talk about unnatural language inference. And the last one will be by Philippe Langlais, who's professor at the Université de Montréal, who is more of a general talk about information extraction, what, why, how, and some challenges. So without further ado, Marco, are you ready for your talk? Or?
Yes.
Okay, so I'll pass. So thank you. Go ahead.
Okay, thanks. Let me try to share the screen. Okay, hopefully, can you just confirm me that you can see the slides?
Yes.
Thank you.
Okay, great, thanks. So, good morning, everyone. I'm Marco Rospocher from the University of Verona in Italy. And today I will present you some work co-authored with Francesco Corcuglianiti from the University of Bolzano on revising a posteriori natural language processing entity annotations using ontological knowledge. The work contributes to the task of extracting quality knowledge from natural language text, in particular about entities. Entities can be semantically characterized by means of several natural language processing tasks. Named entity recognition and classifications, NERC, identifies named entity in a text and characterizes them according to predefined categories, such as organization in the key example. Entity linking associates a textual mention like KIA, its corresponding entity from a reference knowledge base, like the entity KIA Motors from DBpedia, the structured version of Wikipedia. Semantic role labeling identifies the role of an entity in an event or relation according to frame semantics, like KIA being employer and desiring event. These are all different analyses that in many cases are independently performed with different tools, and that in many knowledge extraction framework, like PIKES, on which I work on, are combined together for the goal of extracting coherent knowledge graphs from text. So despite the good performances of state-of-the-art tools on the task they are designed for, combining these annotations might actually result in information that is not always as coherent as Kia Motors organization employer that we have seen in the previous example. Consider, for instance, the two tasks of NERC and entity linking, and two very popular tools used for performing them, Stanford Core NLP, or the NERC tool actually in the Stanford Core NLP suite, and DBpedia Spotlight. In many cases, the situation goes very well, like in the first example, where the mentioned Eric Clapton is correctly tagged as a person and linked to its corresponding DBpedia entity. And these two annotations go on very well together. But in other cases, the results might vary. And in the second example, for instance, the mention of Washington refers to Malivai Washington, which is a former US tennis professional, is tagged as a person, but it's linked to the page of the state of Washington. Or in the last case, the mention San Jose is correctly linked to the Sharks DBpedia entity, but is tagged as a location. And despite the understanding what tool is right or wrong, we clearly see that there is something wrong putting together this annotation, a person and a state in the second example, or a place and a team in the last one. And if we put both information in our knowledge graph, we clearly end up with some incoherent knowledge. So the question is there something we can do about? Well, truth be told, in many cases, each of these tools actually return not only the single best annotation for their task, but they also provide, or can be instructed to, provide other candidate annotation they have considered for the mention, typically weighted according to how confident they are that that annotation is the right one for the mention. So, for instance, in the last example, we can get from Stanford that location is the best annotation, but organization is right after it, just before person, and so on and so forth. And similarly, DBpedia Spotlight tells us that the shark is the best match, but others sorted by likelihood are the city, the earthquake, and so on and so forth. And if we look at this example, we might find much better combinations in terms of coherence, and in particular, also the more appropriate one for this specific example. So the question that we investigate in this work is there a way actually to improve the coherence of the various NLP annotation on an entity mention coming from different tasks? This is actually the problem we will consider in this talk. So let's frame a little bit better the problem. We have a text, which is a sequence of tokens, and some of these tokens identify an entity mention with multiple tasks providing information on that mention. And for each of these tasks, we have a tool that provides one or even alternative candidate annotation for that mention, weighted, and you see from the corresponding bars, according to how much confident typically the tool is that that annotation is the correct one for the mention. And the problem is actually to understand if a combination of annotation is coherent or not, and what is actually the best combination, taking into consideration the coherence between the annotation as well as the confidence of the tools. And to tackle this problem, we propose actually to use ontological knowledge. And more precisely, we assume that the entity denoted by the mention can be typed with all the classes from the ontological knowledge, from this background ontological knowledge resource we are using. And for each annotation coming from the different task, we estimate probabilistically how likely is that that annotation, for instance, the person category from NERC, implies various set of ontological classes from the background knowledge. For instance, the set of classes athlete, agent, and living thing. Class sets are then used to estimate the coherence of the annotation. The more annotations from different tasks implies the same class sets, the more they are coherent. So that we can pick up actually the best combination in light of the original confidence scores of the tools and ontological knowledge. And we call this approach JPARC, an acronym basically for Joint Posterior Annotation Revision with background knowledge. So with JPARC, actually we compute a posterior probability of a combination of annotations, one coming from each different task, conditioned to the information that we have on the actual entity mention we are analyzing, the background knowledge that is typically used by NLP tools to perform their tasks, such as gazetteers, training material, both of them, let's say, for what concern us, are basically black boxes in our approach. And then our ontological background knowledge, the one we are introducing. And we can marginalize basically this probability over the possible class sets from the ontological knowledge. And by exploiting basically some additional conditional independence assumption and further derivation, this basically boils down to estimate some other probabilities. The probability of a given annotation, condition to dimension, and the NLP background knowledge, which we can roughly assimilate or calibrate to the confidence score returned by the tool that provides the annotation, and the conditional probability of having a set of classes given the annotation and the background knowledge, something that can be learned from the data, as I will concretely show in a minute. And of course, by argmaxing the initial conditional probability, we can get the best combination of annotation for the given mention. So to assess the feasibility of the general intuition of the approach, we started assembling a model for NERC and entity linking. So let's start from the NERC part. I recall that with a NERC, we indicate a possible annotation from a NERC tool. So something like person, organization, location, miscellaneous, like the one used, for example, in the Cornell 2003 annotations guidelines. And what we have to estimate is the conditional probability you see in the slide. So the probability of observing a certain class sets of the background knowledge, given the annotation and the whole background knowledge content. And to compute this estimate, we assume actually the availability of a corpus G, where the entity mentioned are the gold annotated both with the NERC types and the class sets from the background knowledge, or let's say more realistically, entities URIs from which we can derive the class sets. And having this information, we can do basically some counting, counting how many times we see that NERC annotation. We also see that specific class sets with respect to all other class sets in the background knowledge. And in this estimation, we have, however, to take into account the fact that the corpus we are using to derive these estimations might be limited in size. And so it is not granted that we will see each possible class sets of our ontological background knowledge a reasonable number of times to perform a reliable estimation. So we have to weigh in some prior, let's say, that we basically approximates assessing the relative popularity of the class sets in the background knowledge. For the linking part of the model, I recall that with AEL, we indicate a possible annotation from the linking tool that is a URI of some entity in the linking knowledge base. And some clarification might be needed here. For linking knowledge base and the linking knowledge base and the ontological background knowledge that we are using are not necessarily the same. The linking tool, for instance, might annotate with respect to a knowledge base like DBpedia, and the ontological background knowledge resource that we are using might be another knowledge base like Iago, for instance. However, in general, we have, or let's say we can define some mappings either at the level of the entities or the class sets of the two, so that it is actually possible to know precisely the class sets in the ontological background knowledge for that particular entity annotations. And therefore, what we can do is that we can state that the probability is exactly 1 if we are estimating the probability of that specific class sets corresponding to the entity, or 0 in all other cases. Some tools like DBpedia Spotlight, for instance, deals also with the case that an entity is mentioned in the text, but it's unlikely it has a corresponding referent in the linking knowledge base, a situation that in entity linking task is typically known as nil. And indeed, nil is typically one of the candidates returned by some of the tools when any entity is detected. And to handle the nil case, as we don't have a corresponding referent entity in the knowledge base, we have to do something different than relying on the same estimation that we previously proposed. And the only other information available to us at the mention level is actually the NERC information. So to do this estimation, we actually rely on NERC data and the corpus G that I previously discussed for the NERC case. And doing some derivation, we can compute the probability of implying a certain class set given the nil annotation using the formula that you see on in the slide. So where the first part is basically something that we already have computed previously for the NERC part, and the second part can be easily computed again from the called corpus G. So the class set in an ontological background knowledge can be many, and we will see some number later. However, for practical realization of the model, we can limit their number by considering only popular classes in the background knowledge. So those that we can see at least a certain number of times in our corpus G. And this certain number of times is basically an hyperparameter of our approach. And this basically means considering only classes in the upper levels of the ontology, and then skipping only the class sets composed of these top level classes that are in the background knowledge. So once we built the model, we performed a comprehensive evaluation to assess if the approach can really help in improving the quality of the annotation used for building a knowledge graph from text. And to start with, we considered 3 different data sets in our evaluation to assess the capability to generalize over different data. All the data sets are annotated with NERC types according to the Connell format and the DBpedia URIs. And the first data set is AIDA, and you see some stats in the lower table, which is a very popular data set for NERC and linking evaluation campaign. And in particular, we use the train split of AIDA, so the part that typically is devoted for training the systems, as the corpus G that we used to learn the conditional probability needed for JPark, and in particular for the NERC part. And the other 2 datasets are meantime and TAC-KBP. They all have differences in terms of number of mentions, distribution of NERC types. For instance, meantime and TAC-KBP does not have the MISC annotation with respect to the AIDA dataset, but we haven't exploited this information in our evaluation, and we actually used the same model built from leveraging AIDA as corpus G in all the 3 cases. We also, you will see also results in the slides for a merged dataset, which is basically obtained by putting together the 3 datasets to better assess the overall performances of the approach. Actually, we built 3 models, not just 1, because we used 3 different background knowledge resources to check the performances with 3 different ontological knowledge. So we used Diago, DBpedia, and Wikidata. You see in the slide the version and some stats about the version actually used. And they, as you know, they are all related in a way or another to Wikipedia. And because of this, we can have mappings between them and the linking knowledge base that was used in the evaluation datasets, which I remember is DBpedia. So mappings which follows from the identity function in the case of DBpedia itself, or from all same as links connecting the entities of the different knowledge bases in order in the case of Diago and Wikidata to DBpedia. Previously, I mentioned the limitation of on the number of class sets considered for each background knowledge resources, and you see here basically the numbers resulting from once we perform the hyperparameter tuning of the approach, where we actually reduce them to 2,000, approximately 2,000 classes in the case of class sets, or in the case of Diago, 35 class sets for DBpedia, and approximately 700 class sets for Wikidata. This also remarks that besides being very related, there are indeed some substantial differences in the ontological information in these three different knowledge bases. To assess the generality with respect to the NLP tools providing the annotations, we considered the two scenarios. The first one, using established and popular tools such as the Stanford NER from the Core NLP suite and DBpedia Spotlight for the linking part. And the second one, using more recent cutting-edge neural approaches, FLAIR NER for NERC, and end-to-end neural entity linking. While the first scenario used tools that might have been outperformed, let's say, by recent approaches, I thought I have to say that this is not always the case in practice, but Stanford and DBpedia Spotlight are still used a lot in practical real applications. And so the assessment with them was important for us, also for giving hint on the actual improvement that people using them in their application might concretely experience by adopting JPark. And there's one difference, substantial difference between the two scenarios. While Spotlight returns also nil information, so not in the knowledge-based information, the neural approach doesn't. So in the second scenario, we were not able to apply the dedicated nil strategy that I previously presented. So the actual research question that we investigated is the following. By applying a joint revision of JPark, can we actually improve the NERC and linking performances of the tools providing the candidate annotations? Or, so for instance, let's say, can we improve NERC performances of Stanford using JPark in a scenario where also a linking annotation is actually performed? And we measured the improvement on three aspects that are typically considered in evaluation campaign: type and link, which measure the capability to predict the correct NERC and linking annotations, respectively, and type plus link, which measure the capability to predict the correct NERC and linking couple for that particular mention. So the right NERC and the right linking annotation. And the assessment is performed using the standard metrics, precision, recall, and F1. And one remark that I want to do at this point is that given the way that JPark operates, it is meaningless to consider measures that specifically address the capability to detect entity mention or the boundaries of the mention. JPark fully relies on the mention that are detected by the NLP tool used, so it cannot introduce or remove entity mention, nor it can change the boundaries of this mention. So therefore, it cannot improve on aspects that are related just to the recognition part of the entity recognition task. So summing up, we created a JPark model for each background knowledge resources. We trained the model, these three models, using AIDA train as corpus G. We used AIDA test A for tuning the hyperparameters. We tested the performances on AIDA test B, the wall mean time, and TAC. And in the first scenario, we compared the raw performances of Stanford and Spotlight, which is the baseline, with two variants of JPark, one that simply ignores nil and the other that addresses nil as previously discussed. And in the second scenario, we compared the performance of FLAIR and the end-to-end neural entity linking before and after JPark, using only the variant that ignores nil, as the linking tool in that case does not deal with the nil aspect. So here are the results for Stanford and DBpedia Spotlight, showing the improvements over the baseline. I'm reporting only the F1 scores for the three measures, but all the results can be found, of course, in the full paper. The statistical significant improvements, which are computed according to the approximate randomization test, are marked in bold. And those are the values using the no-nil variant, while these ones in pink, let's say, are the ones using the nil-aware variant. And this result shows that by applying either variants of J-Park, we almost always observe improvement, and mostly a statistical significant one, on all the considered datasets. And in particular, the improvement is very substantial on the type plus link scores, confirming somehow the capability of the model to predict the correct annotation combination. Concerning NIL, we observed that while the two variants are substantially on par for NERC types, the variant with NILs performs better on link and type plus link. Concerning the background knowledge, I thought some difference can be observed. All three of them produce consistent improvement over the baseline. And finally, the table shows also the maximum achievable improvement. That is the improvement scored by an oracle that always pick the correct annotation if available among the candidates produced by the NLP tool. This is actually an upper bound on any posterior revision of the annotation, and hence actually also on J-Park performance. And we can see that J-Parks settles around 10-20% of this upper bound. And similar improvements and observation also for the experiment with recent state-of-the-art neural approaches, showing that in a joint setting where multiple NLP analyses are performed, the posterior revision of annotation with J-Park can indeed further improve the performances of these tasks on the actual task they are designed for. So the outcome of the evaluation is that by applying J-Park when both NERC and entity analysis are performed, we observed improvement with different combination of tools, different combination of background knowledge resources, different data sets, and thence basically we can positively answer our research question. Before concluding, I would like to share some further observation. The model used for the evaluation, while trained only on AIDA, seems to generalize well over different data, as shown by the good performances also on the other data sets, with generally higher scores for the J-Park variants over the baselines and mostly statistical significant improvements. Another aspect worth remarking is that J-Park contributes positive improvements over the baselines also on the AIDA dataset, a dataset that was actually used to train and develop most of the tools used in the evaluation. The third remark is that J-Park is not specific or hard-coded on some tools, but it works on the candidate annotation. This is confirmed by the evaluation itself, where the very same model was used with different tool combination. So the model that we created can be basically applied as is on any couple of tools annotating with respect to the same NERC types and linking knowledge base. And of course, the model can be rebuilt provided the availability of a suitable corpus G, also for tools using other NERC types and knowledge bases. And finally, J-Park is implemented as a module of Pikes, while the performance of the module depends on the size of the model. In the evaluation, we observed that its computation and required memory are basically negligible compared to the annotations tool. So to conclude, I presented the knowledge-driven probabilistic model for assessing and improving the coherence of NLP annotations. We concretely implemented the model for NERC and linking, and its comprehensive evaluation with various data sets, tool, and background knowledge empirically confirmed the benefits of the approach. As future works for the NERC and linking scenario, one direction concerned density model with other linking knowledge base or NERC types, like for example, tools using fine-grained NERC tools. But a more general and challenging future work concerned the application and validation of the approach to different NLP analysis, investigating, for instance, a scenario where additional tasks are used. In particular, a task that can be considered is semantic role labeling, the task of annotating entities according to their semantic role in a sentence. If you recall the initial example, it means annotating Kia as employer in the hiring event mentioned in the text. And clearly, also semantic role labeling annotations imply some ontological classes. An employer is more likely to go on well with an entity member of classes denoting persons or organizations rather than locations or something else. And similar consideration also for the task of relation extraction, considering the expected domain and range of the relation. So to finish up, here are some of the reference of the work. The website, you can simply access it from the PIQ's website, and you can find there all the results and the evaluation material. The CLIQ-ai 2018 paper, where we introduced the first version of JPark with a preliminary evaluation, and the just published December 2020 Journal of Web Semantic paper, where we provided the complete evaluation that I presented today. So that's it. The slide deck can be accessed from the QR code that you see here on the slide, or by accessing my website. Thanks again for having invited me and for attending this talk. And of course, I'm more than welcome to answer your questions.
Thank you very much, Dr. Rospocher, for your great presentation. So now we have about 10 minutes for questions from the audience. So if you want to ask questions, you can use the raise hand option in the control bar. And I can see that we have one question from Svetlana. So please go ahead.
Hi, Marco. Thank you for the talk.
Hi, Svetlana.
I just have a couple of questions. So I think I was missing a few statistics on the evaluation part. So the assumption behind the approach is that the models disagree. So different tools provide contrasting predictions. So what in your experiments?
On different tasks, so not on the same one.
Exactly. So what from the data sets you used, what was the degree of disagreement between these tools?
So the data set that we used as just the let's say the annotation, the gold annotation basically on the NERC type. For each entity mentioned, there is the NERC type and the corresponding URI from the linking knowledge base. So we assume it to be the gold annotation. So the coherence there basically is granted by the manual annotation that was actually in the data set.
But the ones predicted by the tools, do they disagree so much that it actually there is a need?
The one predicted, they disagree. So can I go back to can I put back the slides? Maybe I don't know if it is my help, but let me try to do it. So in the evaluation, so the top line that you see in each of the 4 data sets basically is the results obtained by the tools, the original tools, while the improvement measures the contribution basically provided by JPark.
So the disagreement, like I'm just trying to understand. So
we don't measure actually a disagreement or an agreement. What we actually measure is that
the improvement is
how they perform their task, because we assume that the gold annotation agrees. So in some sense, we performed, let's say, a kind of extrinsic evaluation of the approach. So we check if trying to put together agreement between different tasks, we are able to improve the performance.
Yeah, but it would work if there is a disagreement. So I was just wondering if you actually measured that there was a disagreement.
No.
Okay, just a follow-up question was, so you had 2 experiments with different tools. Did you also identify how well they perform? So there's more popular comparing with the neural approaches?
Yeah, I mean, in the specific example, the performances of the neural one is higher overall. So if you compare the 2 tables, you see that the overall performance in terms of the quality, let's say, of the annotation each of the tool provides is higher with respect to the Stanford and DBpedia Spotlight combination. The improvement that JPark produced is in proportion is less on the neural one, because they already starts from a very good point, but still by basically considering other tasks and using this information, so not just the task the tool is designed for, but considering other tasks and this notion of coherence, you can improve the actual performance of the tool for its task, which I think is quite interesting, let's say.
So it's basically assembling across the task. Okay, I just give someone else the floor. Thank you.
You're welcome. Thanks.
So Leila has a question. You can go ahead. Mute yourself.
Yes. Marco, can you hear me?
Yes.
Thank you for the nice talk. I actually have two questions. The first is a follow-up to Svitlana's question about the tool disagreement. I'm very confused because if you go back to your results, the baseline only tests a single tool. Is that correct? For example, Core NLP for experiment A.
If you go, let me try to put up again the slides. So let me check. So the table here, you see the first column is basically the performance of Stanford on NERC. The second column is the performance of DBpedia Spotlight on the linking part. And the third column is on the same mention. You take both the annotation from Stanford and DBpedia Spotlight, and you compare them with the gold annotation.
Okay, but the baseline. So, for example, the first row baseline.
Yes.
The first row is in this particular case, it's a Core NLP, correct?
Is Core NLP for type, DBpedia Spotlight for linking, and the combination of the two for type plus link, basically.
So I just assumed that you were taking the agreement, or you were taking different tools, for example, Core NLP and another tool. I can't remember which one you mentioned.
Oh, no. So the idea behind the approach is that we are not, let's say, trying to take different tools for NERC and trying to combine the input from different NERC tools for performing better the NERC tool. The intuition behind the approach is that we have different tasks when you are building a knowledge graph. So entity linking, NERC, semantic role labeling, you use them for building a knowledge graph, and you get different signal, but this different signal might be coherent between them. So basically the extraction, the knowledge graph you can build results in knowledge that is coherent, or they might provide you some annotations like annotating with the URI of a person and typing that thing as a location, for instance, which is conflicting in nature. No? So of course we don't have, let's say, we don't have substantial actions or whatever in the knowledge bases to provide a precise notion, let's say, of agreement or disagreement between annotation from different tools, but we tried somehow to estimate the agreement by looking at a gold standard, at the annotation on the gold standard, and trying to understand which classes from this ontological knowledge are somehow coherent with respect to the input from the different tools for different tasks. So just let me stress it again. The idea is that you are combining tools for different tasks on the same text, basically, and you want to see substantially if using linking when you perform NERC can actually improve the performances of the NERC itself.
Okay. Okay. Would it be something to investigate, to do an ensemble, essentially, to take the output of several tools and then it links back to Svitlana's question of, well, if two tools disagree, maybe, confidence is low.
Now I understand maybe better also Svitlana question. So the question was if there is agreement or disagreement on the same task from two different tools performing the same task. If now I got it right. So we haven't applied it in that case. I think the model as it is conceived and derived from the let's say the independence assumption that we made for deriving the model, I don't think we can apply it as it is, let's say, to the task of measuring the agreement of two NERC tools on the same text. I don't think we can apply it in that way. There are, however, works in which people proposed to use a kind of ensemble approach, like the one you are mentioning, in which they take different NERC tools and they somehow, using a majority vote or any other kind of strategy, or even learning from the data, let's say, they try to understand how to combine the different NERC annotation for different tools on the same text in order to improve an overall, let's say, NERC performance. But I think it's a different task than the one we were interested in this work.
Thank you.
You're welcome.
Hissam, I have another question, but if you want to give the floor to someone else.
If it is a quick question, it would be okay.
Mike, the question is quick. I don't know if the answer will be okay. Let me try. Marco, is there? Because I'm not up to date in the area, but is there? Because what I have seen are identifications or labeling of individual mentions, but is there work on global optimization as opposed to doing local optimization, instead of only doing local identifications, to do global, to take the whole text into account and say, and consider that each mention is not independent of other similar or even different mentions within the text.
Mm-hmm. So let's say I'm not so expert, let's say, on the global task that you are addressing, but I'm sure I've read some works doing that. So not only performing, let's say, a local annotation, but taking in consideration also the information from nearby entities. So the prediction is not just a prediction on the single entity mentioned in the text, but is actually a general global prediction, let's say, on taking in consideration multiple entities that are mentioned in the text. So there are works on that, especially for the linking part. Not so much, I would say, at least not that I know, for the NERC part.
Thank you. Thank you.
You're welcome.
So thank you again, Dr. Rospocher, for your presentation. I'm happy that the last question was not very long, so we can move forward to the next presentation by Koustuv Sinha, who's a PhD candidate at Mila and McGill University and is working under the supervision of Joel Pino and William Hamilton, who is also, and Koustuv is also an intern at Facebook AI Research and is going to present his work titled Unnatural Language Inference. So Koustuv, the floor is yours.
Hi, can you see my screen?
Yes, thank you.
Okay, awesome. Okay, it seems I cannot see you, but anyway, please feel free to ask me any questions. And yeah, thanks so much for giving me the opportunity to talk in this awesome panel. I enjoyed the previous talk really quite a lot. And yeah, so I'm to give a brief introduction, I'm a PhD student at McGill University and affiliated with Mila and Facebook AI, where I'm a research intern. And here today, I'm going to present a work that we are submitting to ACL. So, and basically it's a preprint work, and we want to get some feedback, and basically we want to share our excitement surrounding the work to you guys. So the work is about unnatural language inference. So when you have seen in the recent couple of years that in deep learning, especially in natural language processing, transformer-based language models have taken over, and we have seen a lot of progress from those models, especially let's say from the likes of BERT, Roberta, BART, Distilbert. There's a lot of BERT family architectures that are available right now. And And most of these architectures have kind of like exceeded the recurring neural networks performance in almost all of natural language understanding tasks. Now, the key question that we are asking in this work is that, does the NLU models understand syntax? So, so what do I mean by syntax? So basically, like in natural language, whenever you are whenever your model is trying to understand what it is written in the natural language, we those who work in like NLP and linguistics, we try to understand whether the model's understanding is same as ours, and whether the model is understanding the core underlying syntax of those sentences. And several papers these days have claimed that these transformer language models does understand syntax. So given here, like an example, the people have shown that the attentions in these transformer language models can be mapped to a syntax tree. And people have also like presented several works on like probing neural networks, where essentially you have a linear classifier to probe. And by using that linear classifier, you are showing that your models are able to like understand certain syntactical features of the given sentences. So we are trying to like ask the same question, but in a different way. And we are looking at a particular task in natural language understanding known as natural language inference. So natural language inference is one of the hallmark tasks in NLU. And to give you a brief background about the task, like you are given a pair of sentences, the premise and the hypothesis, and you are asked to predict a three-way classification. So the three-way classification is either the hypothesis entails the premise, or the hypothesis contradicts the premise, or the hypothesis is neutral to the premise. So, and we have seen very impressive performance by transformer language models on this task. So here on your right, I've shown you like a screen grab from Papers with Code with using NLI on the MNLI dataset. And these days we have seen that the best model right now is T5, which has like 11 billion parameters. So it's one of the model released by Google, and that gets like around 92% accuracy. So it's quite impressive. And if these models are so impressive, then they must understand syntax the way we expect them to, right? So before going into that question, we want to ask whether syntax understanding is necessary. So a natural and common perspective in many formal theories of linguistics is that knowing a natural language requires you to know the syntax. So basically, like coming from the Chomskyan theory of language, whenever you claim that you are understanding a particular sentence, you should understand the syntax surrounding it. And knowing the syntax of a sentence, like it can be of several levels, but in this work, we are trying to be very simple. We are trying to say that knowing the syntax of a sentence should be equivalent to being sensitive at least to the word order of the sentence. So basically, let's say in this given example, I preferred the morning flight through Denver. If I give you this sentence in a jumbled word order, then you wouldn't understand anything out of it, because that sentence is number one, ungrammatical, and number two, doesn't contain the syntactical information that the original sentence contains. So people looked into this previously in linguistics and psycholinguistics, where people came up with an effect known as the sentence superiority effect. So this was a nice experiment, which was initially done by James McGill and later from Joshua Snell et al., where in this experiment, like people are shown original sentences, and then people are shown scrambled sentences. And then people are asked to perform a particular task in semantic role labeling. And then what they found out that these like people are generally very, very worse when given a scrambled sentence, which is quite obvious. And it's so much worse that like human annotators are more than like 20% worse than the original accuracy of that particular task. So clearly, like we humans understand sentences because we also understand the syntax surrounding it. And if you basically change the syntax, then humans won't be able to understand it that well. So now we are asking that question in terms of the model as well. So we are asking the question to a natural language inference model, that if I provide a natural language inference model, a sentence which has like scrambled word order, which does not have the syntax that we humans understand, what should a natural language inference model do? So we hypothesize a syntax-aware model might perform in one of the few ways. So when we provide a scrambled sentence, one way could be the model right away recognizes the ungrammaticality, and basically it provides like low probability to the gold label. So basically the correct label, it is unable to predict the correct label correctly, because when it is recognizing the ungrammaticality, it is essentially not performing that well, because an ungrammatical sentence is essentially null and void in terms of pure logic. So the model is unable to perform like well on the gold label. Now, there's another possibility that the model could be entirely baffled and then provide equal probability mass to all of the labels. So the model essentially like gives up its hand and say that, hey, this is a random prediction. Like I'm not assigning any probability to any label. I'm just assigning uniform probability to all of my 3 labels. And then finally, there could be a specific model, like let's say a model which is imbibed the natural language inference principles too well. That model might assign neutral label always, because whenever you're providing 2 ungrammatical sentences, they do not contain any meaning. So 2 null meaning sentences would essentially tell you that, hey, they do not have a meaning, so they do not have any interaction among them. So it should be a neutral label. So these are some hypothetical situations that we present, and we hope that maybe like we will be able to see any one of these like effects coming up. Unfortunately, we don't find that. We find that for many natural language inference models, the state-of-the-art NLU models are invariant to word order. And they are invariant in such a way that whenever you're providing the premise and hypothesis in a different jumbled up fashion, the models are still able to predict the correct label. And this, like, if you see on the example on your right, like in the first example, we are providing like an entailment case where the jumbled up sentence essentially, like, it's very difficult to understand the meaning of the jumbled up sentence. But even then, the models are able to predict the correct answer. And same in case of contradiction. And both of these examples are taken from MNLI dataset on the matched development set. So basically, these are from the test sets from MNLI. And we find this surprising scenario even in the case of like pre-transformer era neural networks too. So it's not like an effect only for transformers. It seems to be like a more general effect for natural understanding models. So, and even more surprisingly, we find that for examples that the model initially got it wrong. So basically, if you recall that the state-of-the-art transformer models gets like 90% accuracy, so there is still 10% of the data set that the model gets it wrong. There exists a particular word ordering for those like data points that can elicit a correct prediction from the model. So given in your right, there's like an example, which is again taken from MNLI test set. And here the original sentence, like Castelrig near Keswick is the best example. A good example would be Keswick near Castelrig. Like this is a simple entailment prediction task, but then Roberta Large gets it wrong. So Roberta Large predicts it as contradiction. Whereas if we provide a different permutation of the word ordering, where the sentences themselves does not mean anything to a human annotator, Roberta gets it correct. And this is what is more surprising in our case. And we term this as like the flip predictions. And we find overwhelmingly that several models exhibit this flip predictions. So you must be now thinking, that must be cherry picking. Like it cannot be. You just took one example, you just took one permutation, and like the model must be performing well only on that permutation, right? So what we did, like we developed like a comprehensive study involving many permutations. So the overall idea is that we take the training data set, we train a model, then we train the model on the original data set. Then we first test the model to ensure that our model gets the state-of-the-art performance or the reported performance of that particular model. And then what we do for each example in the test set, we perform this word permutation for n number of times for each example. So here in our paper, we looked at n equal to 100, like 100 permutations for each example. But theoretically, you can perform any number of permutations to like study the effect in a more general probabilistic way. So now, what is the permutation that we define? So the basic permutation that we define is that no word should appear in their original position. So that means that whenever I'm giving you a sentence, say a sentence of length n, there could be n minus 1 factorial permutations possible of that sentence. Now, if the sentence is longer, then you have more number of permutations that are available. And if it's shorter, then you are restricted to a small number of permutations. So that's why to make the test set challenging, we select unique permutations from this particular operation. And we reject certain samples where the length is less than 5. So basically, if you have like 5 words, then you only have like 5 factorial, like 120 permutations available. So that's too less. So we want to make sure that all the sentences are greater than length 6, and then we select unique permutations from this operation. So now, before like going into the results, let me define like some metrics that we define. So these metrics we call overall as permutation acceptability metrics. And given here on your right is an example of how these metrics are calculated. So let's say in this example, let's say on the x-axis, we have the examples in our data set, and on the in the y-axis, and on the x-axis, we have the permutations for each example. Now, let's say in this toy example, I have only 6 examples and 6 permutations for each example. So now, if by providing these permutations to the model, if I find out that for one example, there exists like at least one permutation which can elicit the correct answer from the model, then we select that particular example to compute our omega max accuracy. So omega max accuracy is basically a threshold which says that, hey, given a set of permutations for each example, even if I can find one permutation that elicits the correct answer, then I select this particular test set. And for examples where I do not get any permutations which elicit the correct answer, then I do not select that in my accuracy. Now, this is a very stringent or very hard baseline, because in the 100 permutations, there could be like just one of the permutations could be chosen at random also. So that's why we have another threshold, which we deem as the omega rand, or the random accuracy. So in the omega rand, we are saying that, hey, if a model chooses at random, and if a model chooses at random, then since there are like 3 labels possible, so at random, a model can be correct 33% of the time. So then if we find more than or equal to 33% of the permutations to be accepted by the model, then we select this particular example in my calculation of omega rand. And then I will get an accuracy for omega rand. Then similarly, in this threshold, like this is a very generic threshold that we define, you can also define x equal to 1, and then you will get like a very the most stringent accuracy, where you say that, hey, given my examples, if all the permutations yield the correct answer from my model, then I will select this particular test set, and then I will report on their accuracy. So essentially what I defined is the max accuracy omega max, which is like the harshest, where at least one of the permutations has to be flipped by the model. And then the random accuracy, where a random baseline can basically just select 1/3 of all the permutations to be correct. And then we also define the probabilities. Now, this is where things get more interesting. So the probabilities is essentially the probability of correctness. That is the average number of permutations per data point, which predicts the correct answer. So in this given example, in the first row, since half of the permutations gives me the correct answer, so the probability of correctness is 0.5. And you can compute the probability of correctness like overall in your data set. But what we did, we split the probability of correctness calculations into 2 cohorts. One cohort is where like the examples which were initially predicted correct by the model. So if you recall, like the Roberta baseline gets 90% correct. So this is the 90% of the data set is in this cohort. And then the other cohort is where the model initially gets it incorrect. So recall, like the 10% of the data set are in this originally incorrect cohort. And then we compute the probability of the permutations to be accepted by the model in these two formats. So this basically like gives us a probabilistic view of like what are the number of permutations that are accepted for this set of data points. So now, defining all these metrics, let us look at some raw results. So we see it's a pretty worrisome scenario. All models are initially trained on MNLI, and then we infer the models on MNLI, SNLI, as well as ANLI corpus. So ANLI is a new corpus which has like 3 different test splits, where each test split is like much more harder than the rest. So in the column A, I have provided the original accuracy on the data set, like the state-of-the-art accuracy. And then we see the omega max values. So in the omega max values, we see that almost all the data set, like 98.7, and here for BART, it's 98.9, almost all the examples in the data set have at least one permutation that can elicit the correct answer from the model. So it's pretty much worrisome, because ideally we would not want any permutation to give me the correct answer, because ideally any permutation would be deemed as irrelevant. So as we defined in our model scenario, if it were a systematic model, then either it would be like a total random selection, or it could be like a neutral selection. So now we also look at the omega rand value. And if you look at the omega rand value, like for Roberta, the max is 82.8, whereas for BART, it's like 83.4. So these two are also pretty high numbers. That means 83% of the data points like exceed the random baseline accuracy. So things are not for chance. Things are essentially this is a quite a worrisome scenario in like natural language understanding processes used by these models, because if they are able to understand even a random word order sentences, then they surely must not understand anything we can claim about human level syntax. Now, we also see the probability of correct is much, much greater than the probability of false. So that means that in the cohort where we have selected the data points which Roberta Large initially gets correct, there exists 70% of the permutations on average. Now this is on average, there could be like even min and max values here, but on average, 70% of the permutations are accepted by Roberta Large if originally the data points are predicted correctly, whereas it reduces to 38.3 to 40% in the acceptance criteria, where if initially you get some examples wrong, there still exists like 40% of permutations that are accepted by the model. So P of F is still not that low, but it's significantly lower than P of C. And we also find this issue even in so the most the significant model is BART large, because BART large essentially gives you pretty bad numbers. So essentially it has the max omega max to be 98.9, and then P of C is 76.2, which is much higher than 76, but 76.8. So it's kind of like similar with the Roberta Large. But if you look at the omega rand, so at random, like BART large is essentially pretty bad also. So now, given this scenario, like we also see the issue even in out-of-domain generalization. So if you recall the ANLI splits that I talked about, these are like a different data set. And when I train on MNLI and evaluate on the ANLI data set, I also found the same issue, where although the issue is a little bit lower than like the omega max is like 93.1 compared to 98.7, and omega rand is much lower. It's much lower. It's 42.4, but still the issue exists in terms of OOD generalization. So now you might be wondering, okay, this kind of results might be just because of these transformer type models, right? So actually, no, these results are also like affect the pre-transformer models as well. Although the overall effect is much lower compared to like the transformer models. So if you look at like in %, the max accuracy it gets on the MNLI test script on our implementations is like 65.8, whereas the omega max is 90.4 compared to 98. And although we find P of C to be much higher, so P of C here is 84.2, which says that given the correct examples, Inference chooses more permutations to be acceptable than Roberta Large. So this is like this scenario is existing even in the pre-transformer era models as well. Now you must still be wondering, okay, hey, this like what is happening? Like I'm not sure about the results that I'm seeing. So we basically plotted the omega x threshold for all the data set, varying the threshold of x, and then we find that at the very like the most worrisome condition is when x equal to 100. So basically that means all 100 permutations are accepted by the model. There still exists around 20% of the data set which contains all permutations which can be accepted by the models. And in the RAND accuracy, like we have around 80 to 70% of the data set, whereas in the in the worst condition where all the permutations are accepted, there we have around 20 to 40%, less than 40, it's around 20 to 30% of this data set. So it's not a data set specific issue also. Like if you look at like the SNLI data set, if you look at the ANLI data set, although ANLI data set is still like much better, because in ANLI you have like less than 10% to be accepted in that criteria. So it is a little bit, but again, ANLI is an out of domain distribution for this training purpose. So that's why it's kind of like a cross data set issue that we are seeing. So now, wait a minute, you must be thinking the label must be chosen by chance. What is the probability of the models? Like what is the probability of the output? So we find that the model entropy for transformers to be quite high, and that is probably one of the reasons why the models are like choosing like the correct label, even when we are providing the unnatural sentence. And we see that the BART has the worst confidence values. So in this plot, we are plotting the average entropy, and it is better if the average entropy is high, but we are seeing the average entropy is quite low in terms of Roberta and BART, where BART is like one of the worst. And here in the plot, the orange bars indicate the data points where the model were initially correct, and the blue bars indicate where the models were initially wrong. And if we compare that with respect to the pre-transformer era models, like their entropies are much lower. Although there is an easy explanation for that, because those models essentially were quite poor in capacity and also model prediction. So that's why, since it's a poorer model, it's expected that their like the output probabilities should also be quite low. So clearly, this is one of the reasons why we are basically looking at this kind of scenario. Now, we also analyzed the syntactic structure of the scrambled sentences. So we wanted to understand what makes the scrambled sentences to be acceptable by the model. So since our scrambled sentences are scrambled like quite well, so we have like pretty low BLEU3 and BLEU4 scores. So basically BLEU3 and BLEU4 are 3 gram and up to 4 gram like word overlap statistic with respect to the original sentence. And BLEU3 and BLEU4 are too low to compare. They are like less than 0.01. So we are comparing with BLEU2, which is a bigram overlap of the words. So bigram overlap meaning that if I give you the original sentence, how many bigrams are still intact in the scrambled sentence? And we find that the relationship is linear, which is quite expected. So as and when you increase, as and when the permutations have at least some common bigrams, their permutation acceptability like increases. But also the permutation acceptability, like the lower half of it, like at least for Roberta and BART, it's still like 65% whenever the BLEU scores are close to 0. So this is still like a large area to improve for these models. Now, we also look at the syntactic structure in terms of a novel post-tree hypothesis. So essentially, this is followed a little bit from the CCG parsing domain, where we try to say that, hey, for a given word, like the model might be looking at signatures of a word. So whenever we talk about signatures, we try to say that a model, when it is looking at a word, the neighborhood signature. So essentially here, I've termed like Mary is a word, but then the neighborhood of Mary might have several pos tags available with some radius, like distance k. And this pos tag distribution might be the signature of this word Mary. And now when I permute this particular sentence, then my pos tag signature changes because my neighborhood changes. The hypothesis is that maybe the sentences which are getting accepted, maybe the overall word signatures are closer to the training corpus than that of the original sentence, or maybe they are even closer to the original sentence. So if Mary has a pretty much novel neighborhood pos structure, then probably that sentence has lower probability to be accepted. And that is exactly what we see. We see that the higher the signature overlap, the better is the performance for the transformer models. So when we look at the ratio, so this ratio is essentially comparing how close the sentences or the mini tree or the word overlap mini tree are for a permuted sentence to the trained corpus versus the original sentence to the trained corpus. So when we look at like ratio greater than 1, that means that in the sentences, the pos tree signature of the words closely represent that of the training corpus and more closer than that of the original sentences. So this is where most of the flips happen. And we see that like for the transformer networks, this higher the signature overlap, the greater the acceptability score. Whereas for the pre-transformer networks, like the acceptability score almost remains the same or like dips down a little bit. So what does this say about it? It says that the transformer language models does understand some syntax. Maybe it understands very local level syntax where it is only looking at a particular word and tries to understand the bigram overlap, or it tries to understand the overall neighborhood signatures of those particular words in order to get the correct answer. So we cannot just rule out that these models does not understand syntax. They do, but in a very, very small rudimentary level.
I'm sorry to interrupt you, Koustuv. So we're about 4 minutes over time. So if it would be great if we can also have some time for the question period. Thank you.
Right. So So okay. So let me just go quickly. So you might also think that I still don't buy this, and neither did we. So we looked into another language, and we saw the similar issue happening in Chinese OCNLI corpus as well. And that essentially negates the issue to be only like a English language tokenization problem. So this problem essentially happens in other languages as well. Now, what is happening, as I initially alluded, that the neural models are probably overly confident and they are probably unable to learn mutually exclusively. So there has been recent work which shows that this mutual exclusivity problem is a big problem for neural networks. I will allude you to like basically read this paper. So essentially what we did, we tried a simple trick where we tried to mitigate the overconfidence of the model on unknown inputs. So what we did is we tried a max entropy training where essentially alongside the original cross entropy loss, we added a max entropy loss where we provided a scrambled sentence and then we asked the model to maximize the entropy over this scrambled sentence. So essentially telling the model that, hey, don't be confident if you look at a scrambled sentence. And then we find out that this simple technique is quite effective. Like we find that the overall max accuracies are reduced to 33 to 34 percentages. And it's a lot of, it's a big drop. So even by doing this simple trick, you can get your models to be quite a bit more systematic. However, there is still room to improve, and we ideally want to see a lot of we ideally want to develop models which actually develop human level syntax. So this kind of scenario shouldn't occur. And then finally, we looked at like human analysis on sentence superiority effect, and we provided the 200 permuted sentences of varying length to human annotators. And even human annotators struggled on it. So human annotators got at most like 58% accuracy to 40% accuracy. And of these 200 permuted sentences, like Roberta essentially gets all of them correct. So there's still like a lot of room to improve in terms of systematic language understanding. So yeah, thanks for listening. And there's a lot of like exciting future works that comes out of it. Like, does this affect only in natural language inference or any other tasks? Or how can we imbibe the mutual exclusivity in our training to make these models even better? Or does language grounding mitigate this effect to some extent? And thanks for listening. This is a joint work with Prasanna Parthasarathy, Joel Pinu, and Adina Williams. And it's a joint collaboration with Mila, McGill, and Facebook AI. Thank you so much.
So thank you very much for your great presentation, Koustuv. We have about 5 minutes for the questions. So you can use the raise hand button to ask questions if you have any. Yes, Leila has the question.
Hi, can you hear me?
Yes.
Yeah.
See, I hear an echo. Koustuv, thank you very much for a very deep analysis. I have a few questions. I hear an echo. Okay, the first question is the choice of the task. So natural language inference is, in my view, more semantic in nature. And so I wonder if there were other tasks. So let me ask a bunch of questions and then you pick. So I wonder if there were other tasks that could have been chosen, because I'm not too sure that it really, the natural language inference really highlights the necessity for syntax. I have another follow-up question, and as I said, let's discuss whichever you prefer. If you scrambled all words, I wonder if, to a certain degree, only the open class words did carry the necessary knowledge to do the inference. And maybe it's a hypothesis, if you had left the stop words alone and only scrambled the open class words, you would have gotten different results. It's a question, it's a hypothesis. Or if you had removed the stop words. Yeah, if you had just removed the stop words altogether.
Right. So regarding your second question, we actually did that. Like, we kept the stop words in the original position and we just like changed the other words, and we still found like the similar issues. So actually in the current in the current scenario, we are keeping the punctuations on the same place, but we also have another experiments where we keep the stop words in the same place and we still find similar effects. And regarding to your first question on like why NLI, like why is this a good task? We think that this is a good task because it gives you like it's a more semantic driven task. I agree, but again, like from the sentence superiority hypothesis, like if a sentence doesn't have the proper syntax, like if like a scrambled sentence essentially doesn't have like any syntax imbibed in it. So that's why if a sentence doesn't have a good syntax in it, so then it's semantic wise, it is like kind of null. So it doesn't have any meaning representations even. So if it's null meaning, so then if you do like interaction between two null sentences, then at most you can expect it to be either random or you can expect it to be predicting the neutral values, but certainly not like the actual original labels that the model were predicting. But there has been like other concurrent works that are coming up on the same idea, and people have seen the similar effects on the glue benchmark, which also consist of like sentence acceptability like corpuses, and also people are looking into question answering tasks as well.
Thank you. The experiment that you did with the human annotations that you put at the end of your presentation, frankly, I asked myself that question right at the beginning of your talk. So I don't know about others, but I would have liked to see that slide right at the beginning, because I was wondering, how does that compare to humans? And clearly this slide shows that humans are annoyed by the lack of syntax. It can't figure it out. Thank you.
Exactly. Yeah. Thanks for the questions.
So thank you very much. Also, I would like to also ask a follow-up question, but unfortunately we are out of time, and we would need to move forward with the next speaker. So once again, thank you very much, Koustuv, for your very interesting presentation. So the next talk would be by Dr. Philippe Langlais, who is a professor in the Raleigh Group at the Department of Computer Science and Operational Research at the University of Montreal. And the presentation title is Information Extraction, What, Why, How, and Some Challenges. So without further ado, I'm passing the podium to Dr. Langlais.
Thank you, Sam. Can you see my slides or not?
Yes. Yeah, you can see it now.
Okay. So thank you very much. So today I will give an overview of information extraction on text. So you can see from the title actually that it's a very high level overview that I will give. So this leads me to this disclaimer. This is a non-technical presentation I will give, and I will express my feelings about my experience as a practitioner in the field for a few years. And actually, I feel a bit like an imposter in doing so, because I know that people in the room, for instance, are more knowledge than I am about the subject. So maybe you can hear my kids at home, but that was not planned. So let's start the presentation. So there are many things actually that can be extracted from text, but I will focus today on works that try to recognize relations between entities in text. So it has been tackled for a long time, and a typical incarnation of that will be that you have a sentence, let's call it a context, and two entities of interest, so let's call them E1 and E2. And the task is typically settled as a classification task. So you have to discover a given relation among a set of existing relations that you have to train your model. So it's typically settled as a classification problem. So currently the best models are actually deep neural networks. And there are several benchmarks that can be used to evaluate your technology, but one which is very popular currently is TACRED. So you have quite a large number of examples to train and another set to test. And the set of relations, non-relations that you have to recognize is 41. And you see the distribution here within this data set. And to give you a feel of where we are in the field, so the state of the art is actually around 75% accuracy. So, so it's not an easy task, even if the set of relations is quite modest, actually. So if you feel interested by this kind of task, I would highly recommend you to read this paper that I'm pointing here, because people are nowadays realizing that the best models are actually very often producing the good output, but for the wrong reasons. So it means that there are still challenges to be addressed for this task to be Today, I will more focus on what we call open information extraction, which consists in extracting tuples or relations between entities without knowing the set of relations of interest, without even knowing which kind of entities we should apply this technology to. So, so just to give you an idea, so you have a sentence here coming from Wikipedia. And the task is to output what we call tuples, which are typically relations between a given number of entities. So here, for instance, we can infer from this part of the text that Jason Charles is known as Chili Gonzalez. Okay, so so the task is to extract as many knowledge or tuples as you can. So you might wonder why this might be useful. So it might be useful eventually in a number of tasks, but typically people used to push that kind of technology to acquire what we call nowadays a knowledge graph. And that's actually how we started to work on that at Raleigh. So in my lab, we had a very small, a toy project, I would call it, called De Facto, where we had to mine information from Wikipedia, in our case, French Wikipedia. And the goal was to populate a knowledge graph. So we ended up with a graph where we have categories, entities of a given category. Of course, you can't see anything on this slide, but if I do a loop on the writers in French, you will see nodes that are categories that are related to writer, like artist, historian, philosopher, and so on. You can see instances of those categories, as well as in red some relations that they have with other objects in the graph. So for instance, a writer is meeting other people, is eventually dying, is writing, and so on. So I mean, it's a toy project, but it was enough for us to appreciate the challenges behind this kind of technology. But a real player are doing really useful things with knowledge graphs. So you likely noticed that whenever you query your favorite search engine, if you query an entity that is known, actually those search engine will come back with a snapshot of information they extracted from their knowledge graph. So from a user's perspective, I really appreciate having this information. But this might be even more useful than just this small digest that is being shown in Google or Bing. But this is an example of a query I did to Google very recently. So I was trying to see whether Google could get my intent of having a pianist. I wanted to ask Google a pianist that would play the same way Tigran Amassian is playing. So I'm asking for pianist here, but typically, so I tried a number of queries, and the best query I found to get my my information was this one. And you see that actually Google is answering with documents that are about Tigran Amassian, but not about the real intent that I wanted to express. One document by chance appeared to have something that is close to what I was asking, but actually they are listing a lot of artists and not only pianists. So you can see that a knowledge graph eventually can help in information retrieval. So to make a link to a presentation we had at the last Evado Montreal NLP meeting, we had Philippe Mesquita that presented us DeepBot. So DeepBot is a company that a startup that is going over the web, acquiring a lot of facts, and they sell an API that you can with which you can query the knowledge graph that they are currently acquiring. So you can see that there is a great interest from big players in there. So now I will detail a bit how extractors are being constructed, and I'm distinguishing here three families of extractors. So so the easiest one are actually built on regular expressions. And there are many of them, but I will only talk briefly about reverb. So typically they are producing quite some noise. So that's why people have been trying to involve more specific technologies. So syntactic or semantic parsing is being used as well in some parsers, and I will describe the OLI extractor. Nowadays, people are more versed into neural networks, and in the last few years, there have been quite a lot of different architectures proposed, and I will just briefly sketch two of them that I found interesting. So let's start with the simplest one. So reverb, it's a 10 years old technology. So the idea, as its name stands, it's a regular expression on verbal phrases that are searched first. So verbal relations in text are identified according to this to regular expressions that look like that. So invented is a verb, located in is a verb followed by a preposition. As atomic weight of is a verb with some modifiers and a preposition. So all those will be relations. So there is a first pass toward the collection to gather those relations. Some filtering is applied, and then it's as simple as finding non-phrases on the right and on the left on those relations. So that's very easy. You only need to part of speech tag your input and you are done. And just to give you a feel of what reverb will output on this sentence that you see here. So because is a relation and 20 March 1972 is a noun phrase, so you will have a tuple like this one. But actually, most of the tuples are really strange. So this one is correct in a way. A Canadian musician resided in Paris. Not very useful, perhaps, but at least correct. This one is a disaster. So France now lives in Cologne. So definitely, it's very noisy. So that's why people have been turning into more elaborate technology. So here I will just concentrate on one such technology. OLI is an extractor that has been developed right after reverb by the same team, actually. So what they have been doing is actually to bootstrap reverb. So they have been asking reverb to go to parse a huge collection of text over the web, and they extracted very safe tuples. They looked at sentences where those tuples, the words of those tuples, so the entities and the relations would appear. And with some filtering, they ended up with 4 million sentences that were labeled according to reverb. And then they used those sentences to train a model. So the model looks like rules that take as input pass between the arguments of the tuples. So here you have a dependency parts of a sentence. So the arguments are festival and that, and the pass is defined by typically the syntactic dependencies that link those arguments. So and actually the system is pretty simple conceptually. So once you find a given pattern in the dependency tree, you just fire an extraction. So here the extraction will say, well, the argument 1 in all the important children of this node, argument 2 will be gathered by reading the yield of this node, removing useless information like adjectives and so on. And the relation is this one. And in that case, it will be B, schedule, the word of the associated to the node, and the preposition here, which comes here. So basically, OLI is a set of such rules that have been acquired thanks to reverb that has been applied initially to extract tuples. So there are nice things with that kind of technology, among which reverb is dedicated to identify verbal phrases, but there are many phrases that are concern non-phrases, and OLI will be able, among other things, to find that kind of relation. So typically, dependency-based extractors will extract more knowledge than proto-speech ones. So the last family I want to pinpoint is neural extractors. So as I said, there are quite a lot of models, but just to give you a feel, one that was working pretty decently was copy attention that has been proposed quite recently. So it's actually settled as a translation task, but one specific, one very peculiar translation task. So the input is actually the sentence that you, from which you want to extract information. And the output is actually the same sentence, but labeled with argument 1, relation, argument 2, and eventually argument 3, 4, and so on. So this is a machine translation engine that actually is being trained. So what they have been doing in their case is to train, it's to bootstrap another dependency-based extractor. So similarly to what has been done with OLI, but instead of trying to acquire a rule, they used a machine translation engine to do so. And because the task is very peculiar, they had to ensure that the output tokens will contain the input tokens in the same order. So they have a copying mechanism for enforcing that. So far so good. It's pretty good technology. At least in some configurations, they managed to show that they outperform the extractor that they use for seeding the training material. But actually, it's not really useful as such, because when you decode your, so you have an encoder that computes a representation from which a decoder will generate some tokens. But you need to run your decoder to get an output from which you can grab your extraction. But if you you need to know exactly the number of extractions that you want to do. So it's not very practical. So that's why people have been proposing slightly more involved solutions. So I will dive into one of them, but the others have been proposing two systems around approximately the same time. The intuition is the same behind both of them. So let me just sketch the intuition behind emoji. So emoji is a brand new extractor. So it's the very same idea here. So you have an encoder and a decoder. So it's again a machine translation engine. The encoder for some reason is BERT. The decoder is the very same decoder that you see here. So it's an RNN. But the idea is that they start with the sentence that they want, from which they want to extract tuples. So they encode this sentence thanks to BERT that gives a representation that allow them to decode something. And so decoding will produce a sequence like that from which they can extract the words that have been predicted, and they will re-inject that for the next extraction. So the model knows which tuples have been extracted already before producing another one. So this is what is being schematized in this loop here. And the model decides whenever he wants to stop to extract something by producing a specific keyword. So that's interesting, because otherwise, I mean, that kind of technology here will produce repeatedly the same kind of output, and so it's not very rich in terms of extractions that are being produced. But here, it's a sort of smarter technology in a way. And the only drawback of that is that you need to re-encode each time you do an extraction. So it's a very slow solution. And actually, if you're interested into that, you can read this paper where they show that it can be done more efficiently. So that's it for what I want to say about the technology for now. But I want to spend some time on challenges. And I guess the main challenge is actually evaluation. So I will spend some time discussing a bit some benchmarks that do exist to evaluate extractors. But I want to pinpoint that before 2016, most researchers would actually evaluate the output of their system manually and say, well, we're good. So, so it's only like 4 or 5 years ago that people have use the good habit of evaluating toward a reference. So this is very good. The first benchmark that has been used is this one that I will describe briefly. There is another one, but which mainly contains this one, so I won't discuss that. At Raleigh, we developed a very specific one that I will describe in a slide, and then the standard de facto is actually this one. So let's discuss the first benchmark that people have been using until very recently. So there are two problems that we identified because at Raleigh we developed that kind of technology, and we were really hard pressed to pick one technology among others that we tried because it's very difficult to evaluate. So we look at the problem of evaluating open information extraction, and we looked at reference that were at benchmark that were already there. So the problem of this benchmark is actually, it's a clever idea. Actually, they used another data set that was designed for semantic role labeling, and they automatically switched that into tuples. So this is very fun because this is a reference that has been automatically produced. But one problem is that there are a lot of tuples that are missing. So it's very difficult to compute recall, even if the benchmark is providing scoring that computes recall, but it's not really recall because there are a lot of tuples that could be provided. So for this sentence, for instance, in the reference, you have only those two tuples that arguably won't be very useful in a given application, but they fail to, for instance, mention those two tuples in blue that I do believe to be useful or at least present in the sentence. And it's not only that, but there are many, since the tuples have been produced automatically, you have a lot of tuples with problems. And so the reference is not really good. Plus, more of an amusement, but we noticed that the scoring function had some problems. So we developed a very simple extractor that you can see here, which says whenever you have a sentence, just split the sentence to the first word. The relation will be the second one, and the argument 2 will be the rest of the sentence, and switch the limit between W between argument 1 and relation. So it's not an extractor, it's just an algorithm that does that. And you see the yellow curve here, according to the scoring function of this benchmark, and we beat any other system that has been attempted so far. So yeah, there are problems with this benchmark. Since then, the scoring function has been changed, but it doesn't change the fact that the reference is not really good. So that's why at Raleigh we said, well, let's try to see what we would like to see produced by an extractor. So we developed this very tiny benchmark, which is called wire 57. 57 is actually the number of sentences we have been annotating. And you can see here one such sentence. And you can see here all the tuples that we have been producing for this sentence. So everything was produced manually. It took really a long time to do so for even a small number, such a small number of sentences, but we did that with the goal of providing a guideline to for someone else to contribute to this resource. So we have some I mean, wire, this benchmark has some specificities. So in most benchmarks, there are words in the relations of the tuples that are what we call hallucinated, but they're not in the source sentence. So it might puzzle, it might bring some noise when you evaluate extractors. So in our case, we mark with by a square bracket all the words that are actually not present in the input. Therefore, we can evaluate differently systems that that are not able to produce that kind of words. We also consider that it's not very useful to have a tuple like who resided in Paris. Not very useful. You need to know that it's about here Chile Gonzalez. So we mark specifically the referent of any pronoun in our benchmark. So this is very important. And yes, that's it. So we also propose the scoring function that doesn't have the problem that I was mentioning previously. So this is not. Unfortunately, it's very small, so that's why people are not using this benchmark. But actually, I have this feeling that people should actually use even a small benchmark like this just to see what they're producing, but because it has been designed very carefully. But the benchmark that is being popular nowadays is CARP. So it's the same data set as the first one, but because the reference in the first benchmark is very noisy and very incomplete, they have been asking Turkers to annotate tuples. So far, so good. It's just that if you look at the resource, you will notice that there is a long tail of relations like those ones that I randomly picked. But it's definitely too specific to be of any interest. So what it means is that this benchmark will give credit to tools that more or less just cut and paste subsequences of the input. So it's not really good. And if you look at the sentences, so again, they took the sentences that were part of the first benchmark, but half of the sentences will be of the form quotation, quotation verb, and person who did the quotation. So if you are training a system, which is typically what you want to do, this is very likely that your system will learn such patterns, and actually because the reference is not complete. Most of the tuples that are available obey this pattern. So it's very easy to increase your performance just by learning this pattern, even if you are not aware that your model is doing that. Plus, in the reference, they don't mark words that are not present in the input. And not even mentioning that the reference is not complete. So I would argue that in this sentence, it's important to know that Bert Vogelstein is a researcher. It's good to know that he's a researcher at Johns Hopkins University. It's perhaps more interesting, but this is also an information that should be extracted. So let me continue with a bit of challenges regarding technology that we embed in open information extraction. So some will argue that they're not part of open information extraction. My view is that they should be embedded. But if you take again the wiki page of Chile Gonzalez, so most of the text actually contain pronouns or definite articles like the, and we estimated that more than half of the tuples that we would extract will be similar to that. So he wrote solo piano 1. So that's very fine, but of course it's only useful if you know that he refers to Chile Gonzalez. So we have been working on that, but typically people do not look at that, and they're very fine of giving credit to a tuple like that, while I would argue that it's of no use in a practical application. So of course you can say you can do it a posteriori, but it needs to be done in a way. Also, it's open information after all, but there is no normalization at all of relations. So if you have 4 sentences like that in your collection, you will end up with 4 different tuples. So I guess that a bit of normalization will be important, and actually it's important because in a reference people have been normalizing in a given way, and if you don't normalize that way, then you will be penalized with those metrics. So yes, it's an issue, and there have been nice papers published recently on this task of normalizing relations. A next issue I would like to pinpoint is that this technique is working in text, which is very fun. But if you take 3 sentences containing the name Paris, you might end up with a mess in terms of tuples, because you will gather together tuples talk about different entities. So here you have Paris in France, here you have Paris in Ontario, and here you have Paris in Paris, Texas. I do believe that we need to conduct entity linking to get useful tuples, but this is typically not handled in that kind of work. The last point is actually even more important to me, is that information is brittle. So if you take something as simple as which country delivers the best wine, so if you query Google, you will rapidly end up with Italian coming first. But some people will argue that French wine is the best wine. Some other people that fortunately we don't have anymore to listen, but think American wine are better. So of course, this is just an example, and we all know that French wine are definitely better. But you know, so there are many cases where you will extract text, and they will say you will end up with an inconsistent knowledge graph. So it has to be taken care in a way. So typically, this is not considered to be part of open information extraction, but I will argue that it should be. Let me finish my overview on a small on a project we have at Raleigh called Allium. It's a collaboration with Erudit. So Erudit is a platform, an academic platform that give access to journals on human science. So you can see here an article that you can read on Erudit. A large part of the collection is in French. And what they wanted us to do was to try to see whether the kind of technology I've been showing you today will help to capture some semantic of the text to improve the navigation toward the collection. So we have been applying open information extraction. We have been applying entity linking to link to DBpedia, BNF in particular, which contains a lot of information about authors, Wikipedia, of course. And we have been designing a lot of different extractors with the goal of improving the navigability of this platform. And we're offering a lot of different views to a given user. So of course you can see tuples with extracted concepts, some of them being linked to DBpedia. We can geo-localize text. So for an historian, for instance, it will be eventually interesting to see what people think about a given place in the world or things like that. And whenever we can link to Wikipedia, we offer a pop-up that distill a number of information we have been able to extract. And the reason I'm finishing on that is that technology is a good thing. Of course, we want good models to do that, achieve good things, but a great source of challenge is actually to use the technology, whatever the level of efficiency of a model. So, it means taking care of the user, and which is typically not considered in the field. So it's time for me to conclude. I feel open information extraction is a really exciting sandbox, and there are many things to be done, and the field is evolving rapidly. I do think that applicability deserves a number of things, among which loving your data, not only your models. Very often it's quite disappointing to realize what the models have been capturing, and you need some care about your data. You need to solve a number of related tasks, whether you consider them as part of open information extraction or not. And you need to measure from which text you need to parse your data, at least if you want to apply it in the wild, so on the web, for instance. Of course, if you have a private collection of documents, it's another story, but otherwise, this is part of the game. So thank you very much.
thank you very much, Dr. Langlais, for your very interesting presentation. Unfortunately, we don't have much time for questions, so it will be only one question that we can have from the audience. So if someone has a question. Yes, Svetlana has a question, so let's go ahead.
Like me. Langlais, thank you for the presentation. I was wondering if you know of any data set for relation extraction from dialogues.
From what?
From a dialogue, like a call center or a discussion.
Yeah, there are data sets like that, but not targeted to evaluate open information extraction. So there you have data sets of dialogues that are available.
Yeah, but not annotated with the labels that we could.
Not that I know. Not that
knowledge graph extraction. Yeah. Do you think it's different from extracting from text if you extract from a dialogue?
No, I think it has some specificities that that needs to be considered, and especially, you know, all what I've been presenting is assuming for granted that we treat sentences by sentences, but actually in a dialogue it won't work. So you need really the context. So that's the main difference, I would suspect. And currently, there are some works that are showing that considering more than a sentence will be useful, but we are at the beginning of that, actually. So in a dialogue situation, it's really important. The context is necessary to do anything useful, which is not the case in the typical OE open information extraction scenario.
Thank you.
You're welcome.
So we have reached the end of our meeting. Once again, thank you very much, Dr. Langlais. Thank you. I need to say thank you to all the speakers, to Leila for hosting, being the chair of this event, and thank everyone for participating in this event. So potentially the upcoming event will be on February, and as far as I've realized, it's going to be NLP in the industry. It's going to be focused on NLP in the industry. So we hope that we can see everyone in that upcoming meeting. So everyone, I wish you a very great day and stay safe. Bye.
Thank you.
Thank you, Essam.
Thank you.